very important concept again in context of properties of matter is what is called an angle of contact. Angle of contact. So suppose this is the liquid, and that's the surface of the liquid. That's the surface of a liquid. And say I dip a small glass tube inside this. Say this could be a glass tube. The glass tube. Right? Then what happens is that the liquid in contact, could assume, in some cases it could be like this only. There could be no changes. In some cases, the liquid in the proximity of the glass tube would be as it is, and there may not be a change. That's one possibility, right? The second possibility is the liquid in the proximity becomes like this. The molecules then take up a shape like this. That's another possibility. They constitute what's called a meniscus. They don't, in the proximity, they don't remain straight. They cave in. They could cave in like this, creating a concave portion here, and this is a convex portion, right? This is my convex part, and this is the concave part. That's another possibility. The third possibility is when I dip this solid inside this liquid, this is a solid surface. When it's dipped inside this liquid, it could get into a shape like this. It could become like this. These are three possibilities. Now, this is the point of contact, for example. This is the point of contact between the liquid and the immersed solid. If I draw a tangent to the liquid at the point of contact, this is the tangent to the liquid surface. This is my liquid surface, and this is a tangent to the liquid surface at the point of contact away from the solid. This is drawn away from the solid. This is a tangent drawn. This is my solid, right? This is the solid. That's the liquid. A tangent drawn away from the solid surface at the point of contact to the liquid. This is a tangent drawn to the liquid at the point of contact. Now, this is my point of contact, say P. At this point, I can draw a tangent to the solid towards the liquid. I'm going to draw a tangent to the solid towards the liquid. What is this? This is tangent drawn to the solid at P. P is the point of contact. Tangent drawn to the solid at the point of contact towards the liquid. This is towards the liquid, right? This is towards the liquid. towards the liquid. Then the angle between these two tangents, theta, this is the angle between the two tangents, theta. This theta is called the angle of contact. Angle of contact is this very theta. Angle drawn to the liquid surface at the point of contact away from the solid. Angle drawn to the solid at the point of contact towards the liquid. The angle between these two tangents is called theta, the angle of contact, right? In this case, do you realize that theta is less than 90 degrees? Do you see that theta is less than 90 degrees? Theta is less than 90 degrees. What do you think is theta here? Theta is 90 because tangent drawn to the liquid surface is like this, tangent drawn to the solid surface is like this, and this is theta equal to 90 degrees, right? Angle of contact here is 90 degrees. In this case, it appears as if, you know, when you immerse the solid inside the liquid, it's as if when you immerse the solid inside the liquid, it's as if it had affinity towards the liquid particles. It's as if it had affinity towards the liquid particles and it pulled the liquid particles unto itself. This is what it seems, right? Qualitatively, it appears that in this case, when theta is less than 90 degrees, you know, there was greater affinity between the molecules of the solid and that of the liquid compared to the affinity between two molecules of the liquid. See, this molecule P, you know, in a certain sense, it detached itself a little away from its brothers on the liquid surface and was more strongly attracted towards the solid. That's why it was as if pulled up, right? Yes or no? And we say that the liquid has wetted the surface. We say as if the liquid has wetted the surface. This is wetting of the solid. This is wetting of the solid. It's as if the liquid has wetted the surface, right? This is a case where the adhesive forces are between the liquid and the solid. This is a case where adhesive forces are more than cohesive force. COH is cohesive, ADH is adhesive. The adhesion is more than cohesion, right? The liquid particles are more strongly attracted towards the solid surface than are they attracted to each other, right? So adhesion more than cohesion, this is what would result, and theta would be, angle of contact theta would be less than 90 degrees, right? Look at this case. This is my point of contact. This is my point of contact. And at the point of contact, this is a tangent drawn away from the solid to the liquid. This is my liquid surface, right? I draw a tangent at this point P, I draw a tangent away from the solid to the liquid surface, right? And I draw a tangent at P to the solid towards the liquid, and the angle between these two tangents would be the angle of contact angle. Do you realize that this angle then is the angle of contact? So this is theta greater than 90 degrees. This is a case of wetting. This we say is non-wetting. Non-wetting. This happens when adhesion is more than cohesion. This happens when adhesion is less than cohesion. Forces of adhesion less than forces of cohesion, this will happen. And as a special case for theta less than 90 degrees, you could have had a situation like this, which is theta equal to 0 degrees. Exactly goes up. this is the tangent. This is like as if theta is 0 degrees. This is like theta is 0 degrees. Theta is 0. Angle of contact is 0 here. Do you see that? Do you get a visual feel for things? This is theta equal to 0 degrees. This is theta less than 90 degrees. This is theta greater than 90 degrees. This is a case where the angle of contact is obtuse. This happens when adhesion is less than cohesion. Cohesive forces prevail compared to adhesive. In this case, adhesion is stronger than cohesion. Adhesion is stronger than cohesion. Right? Do you realize that? So angle of contact depends on very many factors. Essentially depends on the properties of this medium and the solid. So it's not like I give you a liquid and it will have the same angle of contact with, you know, all solid, same angle of contact. No, it will also depend on the solid that I am immersing, because you know that solid could have adhesive forces different from the adhesive forces of some other solid, right? So it will depend on, you know, today I immerse glass, tomorrow I could immerse, say, iron or something else, and you know I would have different angle of contact for the same liquid, right? So it's a molecular property and results out of molecular interaction between particles of the liquid and liquid solid particles. It'll be an interplay of these two factors, right? And just to give you a feel for, you know, let's say for example in this case, why forces of adhesion more than forces of cohesion, I'll get a shape like this, just to get you a very preliminary feel. I would think it's very laymanish, but nevertheless, you know, say what really happens in this case is, this is my liquid. There is this particle P on the liquid surface. Because of this solid, it will experience a force of adhesion like this. Force of adhesion like this, right? And because of its neighboring liquid particles, it will experience cohesion, right? And its cohesion is less, cohesive forces. So vectorially representing cohesive forces like this, which are, this length is smaller than this length, right? Which means the net force acting on this particle P would be the vector sum of these two adhesive and cohesive forces, right? So it's going to be like this. That's the net force on this particle at P. This is going to be the net force on the particle at P, yes or no? Right? Now, the net force at a point on a liquid surface is always perpendicular to the liquid surface. That's a property of liquids. That's a property of liquids. The net force at a point on the surface will always be perpendicular to the liquids. That means this F net must be perpendicular to the liquid surface. So the liquid surface must assume a shape such that this becomes perpendicular to the surface. That means this is along the normal to the surface. This should be along the normal to the surface. So would you not want to mentally imagine that if this was the shape of this curve, right, then this is likely to be the normal? Yes or no? Right? So this happens when forces of adhesion are more than forces of cohesion. Same way you can evaluate if forces of adhesion are smaller than forces of cohesion. Because of this normal, this would be the shape, and this is non-wetting. This is angle of contact greater than 90 degrees. Yeah, why not? See, all that I'm trying to tell you is, a property of liquid is that any point, the force at any point on a liquid surface will always be along the normal to the surface. Will always be along the normal to the surface, right? Ideal fluid. Okay? The net force at any point P on a liquid surface will always be along the normal to the surface at that point, right? Okay. So look at this molecule. It experiences two forces. A force of adhesion, significantly larger than the force of cohesion. Where did this come from? Force of adhesion came from the force that P experienced from this solid. Say it was like this, say. And then it experienced force of cohesion because of similar molecules in its proximity. Say it was like this, right? The molecules are here, so it was, say, like this. So now the net force experienced by P, which is on the surface, must be the resultant of these two, which from parallelogram law is like this. And the net force will always be along the normal to the liquid surface at the point, right? That means this must be the normal at the point P of the liquid surface, right? So for it to be a normal, you would expect something like this. You would expect something like this to be the surface. This is what happens, right?